concerning the production of elements with conductivity and anomalous radiation.
This is my first talk before a meeting, a scientific meeting. I had some questions because I don't get a sense that you guys learn from each other very much. Okay. You saw Ken Schiller's presentation today on EVs. How many of you think that EVs are produced in the types of apparatus that you guys are using? Like, could you raise your hands? Okay, just one person thinks that. So basically, Ken Schiller is here talking, and one person actually accepts what he was saying. So I've been working on plasmoids for 4 years, but I've been working on similar ideas for longer than that because I was studying ball lightning and other phenomena. And so what I wanted to do was talk about my theory and try to explain what Ken Schiller is doing in terms of prior work in the same area. So this is my abstract. I'm going to talk about Bostic, Ken Shoulders, and Matsumoto, and also about the work of Deryagian and Lipson on superconductivity in Russia. And okay, so here's my abstract. Okay, Matsumoto has priority in this area in the production of heavy elements. He produced this phenomena maybe 5 or 6 years ago, and published a paper in fusion technology in November of 1991. I would say that his analysis of these production of heavy elements in the voids and his microstructure analysis of the electrodes is better than anything I've seen here. But it's been ignored for 5 years. Even though Matsumoto has published like 13 articles in fusion technology, I hardly ever hear him being referenced to. And he's not even able to speak at international conferences on code fusion. And he wrote me a letter complaining to me that it's not fair. He should be allowed to speak. This work has 5 years of priority on what you're doing. And I based my theorization on his work, but also on the work of Bostic and Ken Shoulders. So, okay, here. In 1992, I found this image here. It's a trace. It's a trace of what Bostic called a plasmoid. It leaves these ring marks, and this is a paper published in 1981 by Bostic and Nardi, and Bostic is dead, Nardi's still alive. They've been studying these plasmoid phenomena for, Bostic did so since the 1950s. He was the one who first termed this sort of phenomena plasmoid. And out of this developed 2 whole fields of physics. One was plasma astrophysics, which was continued by Alfvén, who's a Nobelist in astrophysics, and by Lerner, by Anthony Perrott, who George Miley is familiar with. These are all basically plasma theorists or astrophysical theorists. Okay, what's interesting about this is that Matsumoto produced the same thing. Yes, this was produced in 1992, or at least he published it in 1992. You can see they're very similar phenomena. This was produced by electrolysis using palladium, and this was produced by electrical discharge using a plasma focus device. Well, plasma focus device is basically just an electrode configuration. It's shaped in a certain way. But Bostic has showed, not Bostic, but Ken Shoulders has showed that this sort of mark can be produced by any kind of electrode configuration. Like Matsumoto just uses a pin, like a metal pin. It's just like a pin you would stick someone with, or a nail or something. Oh, what's interesting about this research, though, is it's had a long history. People have studied this for many decades for fusion research. It's known that neutrons are produced by these phenomena. It's known that there is elemental transmutation here in these phenomena. And it's known that these phenomena travel through the air and do all kinds of stuff. Bockris even speculated about the superconducting properties of these plasmoids. And I'd say there's lots of evidence for that. One of the evidence is simply the cold fusion phenomena itself. Because during cold fusion, what you have are atoms clumping together in ways that they're not supposed to be able to do. Like these plasmoids can travel through glass, they can just travel through materials, and not leave any kind of marking on the window. Okay, like if a ball lightning travels through a window, it doesn't leave any mark on the window. If it travels through ceramic, it doesn't leave any mark on the ceramic. But what it shows is that a very dense, very stable structure is passing through something that's supposed to be solid. In the same way, with cold fusion, what you have are atoms which are supposed to be like solid, for many, generations and hundreds of years, people have thought of the atoms as something stable. But apparently they're able to combine to fuse. And so here's another plasmoid marked by Matsumoto. It was discovered August 25th, 1990. You see here in the middle, what's good about Matsumoto's work is that he does very, very clear and clever work, so he gets very, very clear pictures. Ken Shoulders doesn't do this. Okay, as far as I know, Ken Shoulders hasn't produced anything as clear as this. He's produced markings, but the markings look more like the ones done by Bockris. So you have there's this sort of, kind of like a linear, kind of like a phenomenon here. What I think that is a transverse wave, similar to like the motion of an earthquake or a tsunami. LS is here. I've talked to someone who's an expert in wave theory, like recent wave theory, and asked him what this was without telling him what this was. He thought it was an astrophysical phenomenon. I showed him this, and he said, yes, it's some sort of transverse wave, similar to what you see in like a ring nebula or some sort of astrophysical thing. That's what he thought it was. Okay, here's a picture of one of these ring plasmoids emitting these white lines. Can I ask another question? How many of you have read Matsumoto's articles? Like, let's say you've read most of them? Okay. It doesn't seem like you guys are getting it, so, okay. These are electrical discharge marks. What it shows is that this phenomena, whatever it was, that passed through water, that was emitted by the electrode, that passed through water, that passed through glass, that traveled through the air to get to its nuclear motions. Whatever this is converting to electricity here. And it's similar to, I mean, this is a novel idea. Like, you see the same sort of thing here. With Bockris, you see these sort of lines. You can see the same thing here. Okay. Here's the lines here, and they're kind of faint here, but you can see them clear in his original article. There are these lines connecting these little plasmoids. These are electrical discharge marks between two plasmoids. Here, in this spot right here, Matsumoto calls this a mark of a black hole, because he thought that black holes are produced during cold fusion. He actually thinks that the type of black hole that people theorized, 20, 30 years ago, was produced and left holes. Like they would leave the electrodes and leave holes in his motions and stuff. So there is a faint little mark right here, but you can't really see it. But he calls it's a boring trace. It's similar to the kinds of boring traces that Ken Shoulders showed you today. And okay, this is a ring nebula. So yeah. Okay, I would say, and there's a lot of theory behind this, a lot of astrophysical theories. A lot of people would say this is true. Actually, I got this picture from another article by someone else. This is like a shape of a galaxy, a nebula, and it's like a ring plasmoid. Okay. Okay, so my theory is that okay, my hypotheses, and the one I talk about in my paper, are that atoms are plasmoidal. Everything is plasmoidal, so that an atom itself can convert to light or to electricity directly. And this idea contradicts quantum mechanics, which is why probably nobody here would accept it, except maybe Ken Shores or somebody. It's yeah. Okay, plasmoids have characteristic ways of behavior, no matter the size. So like an astrophysical phenomena, like a quasar, would be the same kind of phenomena you would see in an electrode or in an apparatus. And there's lots of evidence for that in Matsumoto's work. For example, okay, here's a trace by Matsumoto of a beam being emitted by this plasmoid. And it's similar to this one. This is a picture of a galaxy emitting a plasmoid, the plasma jet. See how they're so similar? What it means is that in both of these phenomena, this galaxy and this little tiny plasmoid that's only 65 micrometers across, the same sort of phenomena is occurring. This would be termed a galactic jet. Similar phenomena to this would be called quasars. So what it shows is that a quasar-type phenomenon is occurring here. And if any of you know what a quasar is, it's a conversion of a galaxy itself to a beam of light and electricity in a jet of particles. I'd say the particles are themselves plasmoids, and they go off and become parts of other things. But what it shows is that this very energetic phenomena that astrophysics have recently discovered and are finding occur in electrodes. Okay, this is a picture of a trace. Most Matsumoto and Shores have produced these kinds of marks. This was left on emulsion, a nuclear emulsion, and what it shows is this. What? Can any of you tell me what this shows? Would anybody want to guess?
You were supposed to tell us.
I'm supposed to, but I've published lots of articles about this. Okay, has anybody here read my articles? Can I ask?
Oh, yes, a lot of times.
Okay, so what would this be? Can I ask? You know, but... Or do you?
Tell us.
Okay, so trace, it's a marking left by the plasmoid traveling on the surface of this emulsion. It's very clear. It starts over here and goes down here and goes off like that. And here's a similar one, but it's of a ring plasmoid. Because sometimes, like, plasmoids have a ring structure. Sometimes they have a kind of like a clump structure, similar to the ones I just showed you here, kind of like a galactic clump. A galactic cluster. And here, this is 50 micrometers wide, and Matsumoto has tried to publish this, but he hasn't been able to. It's very beautiful. It's to me, when I first saw it, it was just amazing, because I predicted this in my early papers in 1992. I predicted that Matsumoto would find marks of things hopping like this, and so, okay, what it shows is that when you guys are doing experiments, you have to account for the emission of plasmoids. These things are like Larry Crum, I guess, because according to George, Larry Crum was saying that what I call a plasmoid would have a density of 13 grams per cubic centimeter. These are dense phenomena. They're long-lived. There's these things being produced by. This was produced by discharge, but plasmoids like these are also produced by electrolysis using palladium, by electrolysis using microelectrodes. Matsumoto has shown these things in this article. You have to account for these, because all this substance, which is what this is leaving the device. So, and if you don't account for it, you're missing a lot of the excess energy and stuff that's being produced by these devices. You just show. Oh, this. Okay. Okay, this was a mark left on an electrode, and is similar to those produced by Ken Schiller's too. It's the same sort of mark that was left on the emulsion, but this was left on a copper, if I remember correctly, it was a copper electrode inside Matsumoto's apparatus. So here it is. Okay, this saying traveled on this electrode and left a groove here. This groove is a ditch. I mean, this is what Ken Schiller calls it. Well, he calls it like a ditch. What it shows is that the material of the electrode was taken up to the plasmoid itself. The reason that, okay, this is a common ball lightning phenomena. Ball lightning and these things are similar. They're just two different sizes of the same thing. Plasmoids are micrometer size, and people produce them. Ball lightning are generally necessarily big, otherwise people can see them, and they're produced, they're produced in the earth or in the atmosphere. Or sometimes they come from outer space and stuff. Okay, this is common. Like a tornado, when it's traveling on the ground, it'll often leave these kinds of ditches. The reason why is because a tornado is a kind of plasmoid also. A ball lightning, and a lot of ball lightning researchers believe this. A ball lightning, when it travels, it can travel through a wall and bore a big tunnel through the wall, similar to those that Ken Schiller was showing you today. These holes. What he said today is that these kinds of EVs, he calls them, can travel through a foot of material, leaving a big tunnel. And you got to figure, okay, he did. Okay, he said that this was like 6 micrometers wide. I mean, this tunnel, the material, the target that he used was like 6 micrometers wide, if I remember. It left a tunnel through the entire plasma, through the entire tunnel, through the material here. And in the same way, ball lightning can travel through a brick wall and leave a huge hole, in the wall. And there aren't any residues. Like here, there's no apparent residues. In the same way with ball lightning, when it goes through a wall or a window and leaves a big hole in the window or something, there's no apparent residue. Usually there's no residue of the glass or of the wall or whatever it went through. Sometimes there is. Sometimes what happens is that a ball lightning or a plasmoid leaves a deposit. 5 minutes left. Okay, it'll leave a deposit on a surface, and like Matsumoto has produced, a mark much like the one here, which he tried to publish in his artificial ball lightning article that he presented at the ISCMNS 5, I think. He did an analysis of the ring mark, and he found new elements deposited on the electrode. A bunch of new ones concentrated right here, just like this. And so further proof. Okay. So I guess my main point, since I don't have a lot of time here, I have 2 other things I want to talk about, but I guess what I'm trying to convey here is that an atom is a plasmoid, and like other plasmoids, it converts to light, it converts to electricity, and in this way, like when matter comes into contact with the plasmoid, it'll convert the material to light or electricity, or take the material up into itself and carry it someplace else and deposit it. So wherever it's deposited, you'll find like new elements and radioactivity and stuff like that. And so here's another proof. Like this is like a trace Matsumoto called the superstar, and it's just another plasmoid mark. But what it shows are like particles being emitted here, like a bunch of little ones too. So whatever this plasmoid was landed here and started disintegrating. And what this is here is particle residues. The way it shows is that a micrometer-sized thing can travel through glass, taking with it substance that later reconverts back to particles. And okay, the thing about studying this is that plasmoids show a lot of excess energy. Sometimes, like, people have said that they have, like, you know, much greater energy density than any kind of nuclear reaction, even like today Ken showed us, not Ken showed us, but anyway. Okay, so I guess I'm running out of time. Yeah, I'd like you guys to think about this and give me hard questions about why this can't be. And Miley had a question today about what makes electrons clump together. Like, that was his question to I can't show her or somebody. Ken Schroeder says he doesn't know. There's recent research done on what's called electron droplets at MIT by Mark Kastner. What he does is show that a group of electrons, if it's exposed to an electric field or a magnetic field, clumps together tighter and tighter and tighter. To me, that's just an indication of maybe a way to explain this is that wherever there's light, wherever there's a stress in the plasmoid environment, the plasmoids can clump, and the local time changes and stuff. So those are my ideas.
Okay, thank you.
Could we just ask one question? You talked with Matsumoto about these, and my question is this: one, are these charged? Do they respond to applied electric field intensity or magnetic field intensity? And two, let's suppose your hypothesis is right, that in calculating the enthalpy, we're not counting these. What's the energy in one of them?
I don't know. The reason why I don't know is because the only research I know that's been done on this is with Ken Schroeder's, and he doesn't talk about it. Matsumoto hasn't. I mean, it's known that these things are magnetic. They're magnetized. You know, according to Ken Schroeder's, they have electrical field to them, so they're electrical phenomena, magnetic phenomena. But how much like electricity is tied up into one of these plasmoids? I don't know. So I guess it would vary a lot depending on the plasmoid, because plasmoids vary a lot in structure and stuff like that.
Okay, thank you. Last talk is a short talk. It's a 10 minutes talk about the possible trading related nuclear reaction.
Lewis? When Dr. Jin, who works in our, or at least who visits in our, how do I put this? If you don't get paid, maybe you don't work. But anyway, my unpaid friend, Dr. Jian Jin, and we were discussing the work of Bockris and Mizuno. I mean, I got this backwards. Omori and so on, finding all of these nuclear reactions in palladium. So we were discussing, sorry about that, we were discussing the possibility of the various nuclear reactions that can occur with the various fundamental particles. And so Dr. Jin undertook to determine which of these many nuclear reactions that you can dream up between palladium and deuterons, palladium and protons, palladium and neutrons, palladium and alpha particles, what would be, look at the conservation rules and see how many of these nuclear reactions are valid. And so what Dr. Jin really has done, he's got about 10 pages here of a large number of nuclear reactions. And where the nuclear reactions are metastable, then he also indicates what the decay of those particular metastable isotopes are. Any of you who are interested in that particular aspects, I've got about 10 copies of the paper here. And the reason we're printing it is that hopefully that somebody else doesn't have to go through all of this work to figure. It takes quite a number of hours to do all that. I would, if I had time, I would write a computer program that would just check all of these and go into a table of values, and maybe someone has done that. If they have, we'd love to publish that information as to who has a computer program that will run through check all the conservation rules for any of these particular nuclear reactions. Now, the list of nuclear reactions does not give you any idea whatsoever as to the probability of the nuclear reactions. It just says if you do get that particle into the nucleus, through the Coulomb barrier and into the nucleus, these are the nuclear reactions then that do follow or do obey the various conservation rules. It's no great big contribution except for those who would like to have that kind of information, so we will publish it to save hours of time. Now I guess we've got better do the same thing for nickel.
Absolutely.
And I appreciate the opportunity just to tell you about Dr. Jen's work. Thank you very much.
Okay, now today's section we are finished. So dinner in 7 o'clock in the still same dino. So tomorrow is 8:30. Thank you.
Take it up, right? Take it up, right? All right, Good.
John Ryan.
Professor Smiley. Professor Nadovitz.
Heard your name family
Don't take
around
your
here.
seats.
Nice to put it.
We don't usually work all that hard, but this morning we're going to work hard, and we've got 3 extremely exciting papers to come, and then the big discussion. So let me run from David Nagel, Research Laboratory, Co-Fusion Experiment Theory and Management, Nagel Research Laboratory.
Thank you.
Whatever.
The key thing is to spell navel with an A, not an E. I've gotten badges many times at conferences with the spell. Oh, thank you very much for the chance to be here, and good morning to you. This is going to be sort of a strange talk because there will be a little science in it, but basically it's sort of a coming out party in the sense that it's the first time we've had an opportunity to present the entire picture of what's been going on at our place since the Pons-Fleischmann announcement. And we have been at it since then. Immediately after the announcement, about 24 people stopped what they were doing and took up the hunt. And there are about 12 of us who have stayed with it to a greater or lesser extent over the years. So we really have been paying attention to it. Now, the lab itself, most of you know, is a large, about a 4,000 person laboratory in Washington, D.C., Navy laboratory. And I head what used to be the Solid State Nuclear Physics Division, the Condensed Matter Radiation Sciences Division. So I'm looking at this not simply as a matter of interest, but as a matter of responsibility to the American taxpayer who provides the funding for our laboratory and for my salary, for instance. Now, the talk that I'll give has 3 very, very distinct parts: the experimental part, the theoretical part, and at the end I'll talk a little bit about management. This microphone is clumsy. Can you hear me without it?
Yeah, take it on.
Okay, thank you. So let me start. Let me start with the experimental part, and to put that in context, you know, whether it's a chemical or a nuclear reaction, social interaction, war, or anything, you bring things together in a space and things come out. So one way to organize work in this field, experimental work in this field, is by the input, how the loading is achieved, and by the output, what measurements are made. So we have, you know, the relatively gentlemanly way of loading deuterium or hydrogen or other isotopes into materials that is thermally. We have the more aggressive electrochemical means, and then we have what I call the Department of Defense approach, that is to shoot them in, whether they be from an ion beam or a nearby plasma or whatever. Now, of course, the measurements in this field have fallen into two broad categories, heat and other things. The other things can be divided further into energetic quanta, isotope and elemental analyses and the like. And we have worked broadly in the area of electrochemical loading and heat measurements and kinetic loading and charged particle measurements. Okay, so I'll show you a little bit about that at fairly high speed, and I don't mind taking questions during the talk if it suits you. So the kinetic loading aspects fell into a series of studies. One of the initial ones was to use sub-kilovolt deuteron beams to load titanium and look for energetic particles. We saw something, I'll show you an example of that in a moment. We followed it up with 2 to 3 years of work in an attempt to reproduce it that had very, very mixed and very limited results. At that point, we switched to an attempt to redo Jan Kucherov's experiment, worked on that for a couple of years, and we got some statistically significant gamma ray spectra, but nothing that really jumped right up out of the noise. And we finally had to abandon that for lack of funding. And the final thing we did was an attempt to reproduce Tom Claytor's experiment, which you'll hear about in detail on the next talk, and we were unable to get any tritium production there. So going back to the ion beam, the kinetic loading, this is a one view graph presentation of the setup and of the results that we got. It's published in a memorandum report, the cover of which is here, 1991 report, and if anybody wants a copy of that, just let me know. The experiment was to load a titanium foil here with 350 eV deuterons and to look immediately behind it with an energy-sensitive particle detector. And what we saw is an example that's indicated on the right. You have energy, MeV on the top, and counts per channel here, and we saw a very, very strong peak here around 5 megavolts. Now, we got this a few times. We interspersed absorbers there and saw the peak attenuated and shift. We changed the conditions on the detector. We did a lot of experiments, and it looked as though it was a triton, okay, 5 megavolt triton. And this is what I say set us off in our 2 or 3 year adventure to try and reproduce it. We never got back to a point where we had strong signals like this, although, as I say, we had some things in the subsequent work. Now, switching to the electrochemical loading, early on, Deborah Rollison did some work when she did loading of palladium, and this is all palladium materials, with D2O, and saw some isotope shifts, which are now probably recognized to be molecular interferences, so that's gone by the board. Talbot Chubb, most of you think of in terms of the Chubb and Chubb ion band theory. I'll mention that in a bit, but he's an experimentalist at heart. He led an effort to reproduce the boron-Leo experiment, the Fusol experiment, and that really never got off the ground for corrosion product reasons, and so the experiment was never really functional and didn't lead to anything. We had a significant Office of Naval Research funded program that was aimed at milliwatt level calorimetry in very clean experiments, and then another X-ray diffraction experiment. So what I'll do in the next few minutes is show you what's the essence of what went on in each one of those. The calorimetry experiment was not much of an advance in terms of the calorimetry, but we did a very, very good job on the material side of it. We have, beside my division and the chemistry division, an entire materials division. They're well equipped, and they were able to bring to bear some, good machinery already in place in order to make electrodes for the experiments, the kind of electrodes that were manufactured within the lab. This is an example here, about 4 millimeter diameter, and you see a few centimeters long, and it was machined without oil. Great care was taken to keep it clean. You have the grooves here for the 4-point resistivity measurements. We did the spot welding with palladium contacts to avoid contamination. It was a very, very careful piece of work. There was a tremendous amount of characterization work done. As indicated here, the various kinds of microscopy, diffraction, hardness, and there is a great deal of data, just page after page after page in the report of grain size studies, annealing, boron concentrations in different levels, and I don't need to go through it in detail. All I would like to do is convince you that we brought to bear transmission electron microscopy, everything we could in order to really understand the materials, because the materials are, of course, at the center of the mysteries in this field, the creation of the right conditions. And the bottom line is that despite all the care that we took in making electrodes and characterizing them, in doing dynamic loading experiments, and it was a campaign involving several people over the better part of 3 years, we got no excess heat. Okay. And in fact, our own experience in general in this area is that the closer we look, the less we see. Okay. And that's true both on the kinetic loading side and on the electrochemical loading. So if you want further details on this, I'm sorry to roar through this, but this is just a sampler, so to speak. There's a 10 millimeter thick report we put out earlier this year, and again, let me know. And you're not going to see any excess heat in it, but it's a reasonable job on the materials and the characterization. Those samples went to a number of places, China Lake, SRI, Utah, and some of them are still available. Now, switching to the X-ray diffraction experiment, since loading is central here, we said to ourselves, why not study loading in situ dynamically? So what we did was make a cell that was a centimeter in diameter and had in the center of it a millimeter diameter palladium wire, and we took it to the synchrotron radiation beam lines at Brookhaven, the National Synchrotron Light Source is indicated here. And it's remarkable but possible that you can take and stop that beam down to about a 10 micron cross section, and there's sufficient intensity in it that you can get X-ray diffraction patterns off at a fixed angle in reasonable time. So the way this works is that you have white light, that is a continuum of radiation coming here, and of course Bragg's law, lambda equals 2d sine theta. If you fix theta is fixed here, you can scan the d spacings that you're searching for in the material by having different wavelengths culled out of the polychromatic radiation in the incident beam. So it was possible to measure, I say, during the loading, right through the cell, at the edge of the electrode, and then 100 microns in. So the human hair looks like this. So we're stepping in at diameters about the scale of the human hair and following the diffraction peaks as a function of time during the loading. On the edge, you get energies over a broad wave range here. You see the photon energies from around 10 to 80 kilovolts. And the peaks are uniquely associated with particular lattice spacings in the crystal because of that Bragg relationship that I just indicated. Now, if you go to the center of the crystal, the attenuation due to going through the palladium wipes out the low energy spectrum. This is the palladium fluorescence, so that's ignorable. But you still see lines at high energies that are useful for watching the dynamics of the ingress of the deuterium into the electrode dynamically. And there are slight but readily measured shifts between the alpha and the beta phase. Okay, so here the one particular peak, the 200 plane peak, there's a slight shift here. It doesn't look like much on this scale, but if you blow it up, it's easily measured. So it's possible to get information such as this, where as a function of time, this is out to 1,000 minutes, you can study the variation in the volume, the lattice behavior. This is expressed as a percent change. This is 10% change relative to the starting material, and you can follow it at the edge or in the core and watch the alpha phase go away, the beta phase grow in, and so forth. And if you're interested in this, or you're going to be in Japan next month, this will be presented in detail. The point of showing this is that we have tools available in order to do studies that are supporting work for cold fusion research, and at the same time, if cold fusion didn't exist, these would be worthwhile studies. In fact, that's one of the themes I'd like to leave you with. The funding situation globally in our lab in this area has gone to zero. We no longer have anything funded. It's too expensive to bootleg in general, although the interest is still there. So that what we're attempting to do is to use some of our internal basic research money to do work that's germane to cold fusion, but at the same time legitimate research and development on hydrogen and its isotopes. Turning briefly to the theoretical and the computational situation, we have a theoretical group headed by a fellow named Dimitri Papansantopoulos, and they've been studying the electronic structure of hydrogen and deuterium and palladium materials for a long time for superconductivity reasons. Okay, so we have a background of about 10 papers on that material system. Now, when cold fusion came up, chemists did some DD interaction studies. The Chubbs developed their ion band state theory, which is the only two places it's controversial is inside NRL and outside NRL. And the arguments that we had a meeting in my office recently where I had two things to say. One is, if you know Scott Chubb, it's a little hard to find the volume switch. So I had two things to say. One is, we can hear you, Scott, and the other is, let him finish his sentence. But anyway, it's normal from my perspective. It's contentious, it's argumentative, but it's the way science gets done. Now, probably not known to you, we have a fellow, he's a professor at Huntsville, named Jim Baird, who's working on the theory of hydrogen diffusion, which is still, from my perspective, a essentially unsolved problem. If you have a niobium sample, in the time that it takes, say, a carbon or an oxygen atom to diffuse a micron into that niobium sample, hydrogen will go 10 meters. And it's a very, very interesting physics problem. And then more recently, we've begun a theory review. So I'll mention a few things about each one of these very briefly as I finish up here. The isotope effect on diffusion of hydrogen, deuterium, tritium, and metals is what I said, Baird has been studying. This is a standard Arrhenius plot, 1 over T versus the log of the diffusion coefficient. And this is data out of the literature in the points, and then the theoretical work in the line. So what we basically think is that the model Baird has conjured of a hydrogen isotope, or say a proton or a deuteron or a triton, sitting in the potential well in a lattice, and then absorbing a phonon and getting kicked over the barrier is in fact the essential physical model involved here, and that he's going to, he's tested this against about half a dozen metals. Some show inverse isotope effect, and anyway, so far so good. And again, I offer this as an example of research that if cold fusion didn't exist, is still good science, and it is germane to cold fusion. Now, in the theoretical review, many of you remembered a nice paper. We have one of the co-authors, Young Kim, here, that was presented at one of the international conferences. And it was a broad survey of the theoretical situation in the field at the time. And now this is, what, 2 or 3 years old or something like that. And things have evolved. So we recently hired on contract a young fellow named Robert Rudd to sequentially go through the various theories. So he's producing a set of reports. He's looked at Hagelstein's theory, he's looked at the Chubbs theory, he's working on Preparato's work now. That's fairly entertaining. So what I'm essentially making you aware of is that we're in the process of an updated theoretical review of each one of the really serious theories that are brought in this field. And the reason we're doing it is because, you know, at some point, I believe what we hope for will happen, that this business will turn a corner, the corner analogous to what happened with high temperature superconductivity in 1986, where even though we didn't understand it, in fact, still don't understand it, you have a recipe, you can make use and do useful things, and start to really focus on the optimization from a practical viewpoint and the understanding from a scientific viewpoint, two, of course, being related. So finally, how much time do I have left, please?
You've got another 7 minutes.
Oh, wonderful. So let me say
that includes the discussion.
Well, we're almost done. I should say a few words in the last few minutes about the management aspect, and I've essentially tipped my hand already in that what I'm trying to convince people in the government of is that if work on cold fusion is funded, it isn't going to be rolling the taxpayers' money. You either win or you lose everything. That there is a tremendous community that has been doing research and technology development on hydrogen, and there was a meeting last month in Switzerland. It says, it's hard to read, International Symposium on Metal Hydrogen Systems, Fundamentals and Applications. There's a series of meetings. The World Hydrogen Energy Conference, the 10th one was 2 years ago in Florida. The 11th one was in Europe already this year. And whether it's propulsion of a space shuttle or hydrogenation of petrochemicals or the storage of hydrogen in metals and alloys for the propulsion of vehicles, there are a tremendous number of potential applications with some really good scientific problems. For instance, the people who worry about hydrogen storage for vehicle propulsion will add a few percent of a sixth material, say, to an alloy in order to tune the ingress and egress temperature, and that's just not understood. You know, is it an electronic structure effect? Is it a defect effect, or what it is? And I just pulled this out. We do have, in fact, a hydrogen storage study, totally independent of cold fusion, going on at our place, and it's one of many, many things. So what I've been doing, rather sporadically but relentlessly, is trying to get the people in the government to sign up to this picture. There are really 5 possibilities, from my viewpoint, in what will happen in this area of low-energy nuclear reactions. And, you know, it's possible that everything, all 2,000 plus papers, all the people, all the reports, you know, with adequate instrumentation and good calibration and all of these things, despite the lack of reproducibility and lack of understanding in many cases. Okay, you know, theoretically it's possible it's all going to be mistakes or lies. Now, what I'm saying to people is that I can't dismiss this any more than I can dismiss supernova 1987, which, while uncontrollable, irreproducible, and not understood, was real. Okay. Yeah. Okay. So officially, I have to act as though I'm up here at the vertex. Okay. But you know, just between us, that's far from the case. And while I'm not trying to argue within Washington about the reality of it, I am trying to argue for the need to study it. So whether it turns out to be arcane science, that's just a little scientific effect, something that works but it's useless, something that's militarily useful, like you're not going to make money with a tank, but you should go buy tanks, or actually commercially useful, is to be determined. And of course, the fundamental argument is that if, as many of us think, nuclear reactions are involved, whether it's energy production, the production of tritium for nuclear weapons, the destruction of nuclear waste, or production of important materials, any one of these is reason enough for the government to put a relatively small fraction of the $70 billion it spends on research and development every year into this. So the last view graph is a recounting. Now, I really shouldn't show this because you're free to conclude at the end of my discussion of this biograph that I'm a really lousy salesman. I've been to the White House Office of Science and Technology Policy, to the Defense Advanced Research Project Agency, $2 billion a year budget, to what used to be called the Defense Nuclear Agency. You know, go down and brief the director, he says, thanks, Dave. Been to the Admiral who runs the Office of Naval Research, and then given other talks, Institute for Defense Analysis, a public lecture, university seminars, and the bottom line is nothing in terms of funded programs, okay? So the reason I think I'm on the agenda here is to tell you a little bit about what went inside our laboratory, yes, but more than that, to let you know that the U.S. government has not exactly been asleep, and that despite the lack of success today, we're working the problem. Thank you very much.
Just before I call for discussion, you were talking about the Naval Research Laboratory work. Now, there's also this work Dr. Spark presented, which was done under Navy auspices, and Milburn Miles at China Lake, all that. There are other Navy labs.
Oh, absolutely. So you have ONR here, and under that you have NRL, then you have other Navy laboratories, and that's a very good point, John, that we've not been alone in this.
Does it make sense to think in terms of having a on-sub device for amelioration of radioactivity, like getting rid of some of your spent fuel elements, or is that possible to handle it that way?
It's theoretically possible, but it's not attractive to me at the moment until the question I asked yesterday about being able to take care of all of the isotopes is answered. So the sequence is, you know, to nail it as an effective land-based, power-consumptive, yes, approach, and then whether or not it can ever be made small enough in size and sufficiently low power to be practical. You know, I'd settle for an onboard cold fusion energy generator. Okay. I mean, just not produce the radiation.
Does ONR support cold fusion research in any of the labs?
Not anymore. That program that resulted in all that metallurgy and the loading and electrochemical measurements I mentioned was an ONR program, but that's dead now.
Yeah, quickly. Approximately how many cathodes did you actually produce with the machinery? Just the number.
Oh, dozens.
A dozen, like 50 or something?
Yeah, something like that. And flat plates. And
Yeah,
The other points?
yes.
Two philosophic ones. You're talking to all these agencies. Maybe you need to get a team of people, ones who signed this paper you were circulating to go with you, so you have a little more support, or do you need that?
Well,
maybe it's a question is, how can the community help you in Washington?
Yeah, from my perspective, it was hard enough to arrange those meetings that I couldn't have gone in with a large group in general. Okay, so from a practical viewpoint, and I know most of these people, so what I did was all right. But we have to, as a community, keep pressure on, especially on the DOE. You see, the DOE wasn't on that list. Why wasn't it on the list? I went to the person who mentored Martha Krebs. He called up Martha Krebs, and he said, listen to Nagel. And I met her at a meeting. She said, hi, Nagel. So anyway, my response to that is to, just keep pushing on the system, on the political level, on the personal level, every which way.
I think we better leave it there, it's just on time.
Yeah.
That was 1 minute over. So I guess the next on the program is Tom Claytor, and pretty.
Right, see, I'm Tom Claytor, and a few of the collaborators. You can also find this talk or a similar talk to this on our World Wide Web page, so you can look it up and get a reprint off. We'll be talking today about this tritium evolution from palladium alloys. First of all, we'll just go through a couple of tritium facts. Tritium is a radioactive isotope of hydrogen. Okay, it decays, and that's what makes the detection sensitivity so great. One of the things that we're interested in here is this 30 kilograms, $30K per gram. And there are plans, dual-track plans right now for APT, accelerated reduction of tritium, or reactor production of tritium. At the potential cost is $3 billion probably in 2005. So if any of this is pretty preliminary research, but there is quite a bit at stake. So it's not an intellectual exercise, but it does have some ramifications. There's some other things going on too. State Department's been funding Russian scientists to do almost cold fusion. This is one of 3 proposals that, the 2 other proposals were approved by the State Department. I reviewed 3, and 2 went to, all 3 went to the State Department. 2 were cut out by bureaucrats who won't really tell me why, but the Russians are getting some money from the U.S. We can't. They can't. So, this is kind of an experiment summary on what we've done so far, and this covers pretty much the last year and a half. Some of this we talked about last year, and the big problem here is that with the pure palladium batches, we get a batch in, we test it, it either produces some tritium or it doesn't. And we're not really sure why. We analyze it, we look for tritium impurities, we look for impurities in the material, and things don't correlate very well. In fact, one of the things that we tried doing was this. We tried just plotting the total impurities versus the tritium output, and we didn't have this particular point at that point, so it looked pretty good when we got that point. That sort of dampened our enthusiasm for it. But what this really means is that probably impurities are important. There are poisons and there are enabling impurities. So what we tried to do was go into this alloy study, and the alloy study is in the middle. We have a number of these alloys. Now these alloys with asterisks are the ones that have done anything. They produced a little bit of tritium. these guys, the popular alloys, beryllium, lithium, and nickel. Nickel because of tantality, and some cobalt because it's magnetic. These are alloys that we have prepared, but we haven't run yet. And maybe some of these are spurred on by Hagelstein. Okay, there's a few things in here that, and we also have a few alloys that we haven't prepared yet, but are being prepared. So the sort of the interest is indicated by the number of times we've run it. We've run this one 12 times, 2, and these other metals, which we had to run for control experiments, the platinum for control, the tungsten for control, were also indicated by Romanov in Russia that he got a lot of tritium out of some of these hydride formers. We haven't seen anything out of these. So we concentrated on this particular alloy here. Out of 12, 2 were controls, 8 were from batch 1, and then 2 were from another batch. And of the 8 from batch 1, 4 of those worked well, and the other 4 were about 3 times lower. So that kind of gives you the idea that it's not very reproducible yet, but there are mitigating factors in that. Of these 3 batches, 2 of the batches are somewhat segregated, and 1 batch is homogenized. So of the batches, the 2 that are segregated, those are the ones that actually produce a little bit of tritium. The one that's homogenized doesn't produce hardly anything at all. So there you have a pretty clear-cut materials variability indicator, and I think that's, this is really kind of insidious for the field, because if this is really true, we have a ternary system, we can have segregation, we have a lot more variables than you might expect, and that's just goes with the territory, I think, and also it's been indicated that we have that tremendous batch-to-batch variation, and that's pretty typical of that. Okay, this is the canonical tritium measurement system that we have. We have the plasma cell here. We flow the gas around through the cell. We're putting on a mass spec so that we can look at the gas concentration now and the impurities in the gas. We also, in the last year, put this little water collector system on, so we determine what the tritium is in the D2 independently, and then compare it to the FemtoTech in all cases where we've looked at the drop in the reading and we've compared it. It's been within, say, 50 ppm of what we expected. So that's pretty good. I don't think there's any artifacts in the system here that we can't account for. We also have a cold trapping. We are putting in carbon dioxide additions, and those are converted to water, and we can cold trap those and count those, and I'll show you some results from that in a little bit. Okay, with the plasma impingement method, okay, we just apply a large voltage between a wire and a foil, or a wire and a wire. The peak powers are up to 10 kilowatts, average power 2 to 4 watts, and as I say over here, the pulse parameters are really uncritical as long as the palladium is hydrated. And that's the trick here. At pressures of 200 to 350 torr, this plasma will go up the wire about halfway. The plasma is blue rather than bright pink. We can't really get the pink plasma, which is singly ionized D+. That goes right into the wire. The blue is less effective. The big problem with this experiment is the wire temperatures tend to run around 60 to 150 degrees C, so that means at this pressure the D to M ratio is 0.55 to 0.01. So if we overheat this by trying to put more power into the small wire, what will happen is that we'll just fall off the stoichiometric curve and we'll deload the palladium. So that's always been a problem for us. These are some of the cell configurations: multiple wire, single wire, plates with high pressure behind them so that we load the plate up. And right now what we're using is this very conservative of material sort of configuration with a loop of wire. We have a little wire. There's only about 30 milligrams of palladium in the system. This has its disadvantage in that when you have a lot of palladium in the system, these plates are like 2 grams, you can watch the loading. But with this small system, because of the volume, you can't really see the loading, so we're kind of flying blind in that regard. And I think we can overcome that to some degree, but right now that's still an open question. These are some results that we had from last year. The colors really aren't coming out too well on this, but what you see are backgrounds here of platinum hydrogen, deuterium, platinum palladium hydrogen. These are all background runs which are just very close to the drift rate of the loop at that particular time. And these are palladium and deuterium foregrounds. And so what you see is when the plasma is switched on, you see a little glitch here, and then it starts to go up. Plasma's off here, goes up, plasma went off to there, goes back up, and the plasma's off there. Then we're pumping up the pressure in the system. And when you pump the pressure up, you actually get the quantitative amount of tritium because the cell is less efficient at lower pressures. So the ionization gauge doesn't really give you the right reading down here. All the slopes are pretty good. So the other thing that you can see from this particular graph is that there are different slopes when we're running under different conditions. And a lower plasma, if we lower current in the plasma here, and if we raise that current, we do tend to get a little bit bigger slope. But again, if you go too far, you'll just start dehydrating the material, and what happens is that the effect goes away. A lot of people tried to encourage us to put in H2 gas additions, and we haven't seen any enhancement of tritium rates from those. They've been pretty much the background growth rate. And so this is just the H2 versus E2. And we've done this a number of times, and we really don't see any enhancement with hydrogen. One of the other tricks that we've tried, and this was again originally what we had done was put in argon into the system, because argon will apparently at lower pressures will help you get the D+. And so we've done a number of gas additions. Well, the only gas addition that really has done anything has been the addition of CO2. And this is a plasma cell from a particular material. You turn it on, it's a very weak producer, nothing much happening here, until we add 2 torr of CO2 and 280 torr total in the system, so it's a very small percentage. And what has happened is that the tritium output has gone up by about a factor of 5 here. And also the pressure has dropped. Now the pressure will drop down as this is converted to water to 278 torr. But it continues to drop, and that means that what's happening is the material is hydride. And so it actually hydrided probably prior to that, but it continues to hydride. And this is one with a large plate, so we can actually follow this. And then we pressurize that, and it gives up to this value here and make our quantitative measurement. Now, there's another feature to this. If you have a system where the wire is fully hydrided and the rate is going off like this, which was another one we did right after this, and you add the CO2, there's no change. So really, the CO2 isn't a panacea. It's just it's a hydride aider, but doesn't seem to help the rate, because whatever the rate is in that material, that's what you'll get. Okay, now I'm going to. Those are all results with the pure palladium wire, and the problem with pure palladium wire was we could not get consistency from batch to batch. The supplier would send us one batch, it would work well. We'd order another batch from that same lot, and it wouldn't work at all. So we went over to the palladium lithium system and all these alloys. And this is a typical result from palladium lithium. We've run a couple of these. There's just a small decrease in the output. So over 100 hours, you can see this one's just dropping down. And kind of compare that to the other one. You can see this one went up a little bit over 100 hours. Okay, so that's lithium doesn't seem to do anything for us. And after looking at like 50 or 60 of those, you get the idea that when it goes up, it's pretty unusual. Here's palladium beryllium. Again, you're going down a little bit, and the pressure as it goes up by about a tenth. Okay, so that was one that is out of consideration. We ran a number of these nickel samples. This is a 1.1%. There's also 2% nickel. Again, just sort of drifting down over time. These are 6-day runs. Now here's sort of the break that we got. This is the palladium rhodium, and I think there's a paper published in Fusion Technology that I saw. Okay, on palladium rhodium. Well, we had this a while ago, but this is again a confirmatory sort of thing. So here we have it's sort of flat. That's 150 hours. Didn't really drift down. That's good, but it's not too spectacular. And then it pops up at the end. It pops up a little bit more than the other ones. Well, this is at 10%, and so we tried lower alloys, and I'm going to skip about 6 months worth of work back here. And so what we came up with was palladium, rhodium, cobalt, which we have 5% palladium and 5% cobalt. And here's some background runs. This again is hydrogen with this particular material. This is hot D2, where we've initially started with a low current, and then later in its life we've raised the current so that the material is dehydrogenating. And these are a couple where we've intentionally kept the current low and kept it cool, so that what we're doing is we're just generating and treating. But you can also see that there's a different slope here and here, and I think there's some slight dehydrogenating of material as it goes on. This is again 120 or so hours, so about a 6-day run for each one of these. And again, there's 4 of these sorts of runs that have been good, and then a couple of these control runs, as well as some runs where we've just heated the material up electrically. Now, recently what we've done is this sort of thing, and this is again the same batch, starting off here, running it under these conditions, but it's fully hydrided, and it's fully hydrided because prior to this we spent about a week cleaning up our loop, and it turns out that after these runs, after a number of these runs, and I'm not really sure why we should have something build up in the loop, but we do. We have a hydride inhibitor that's in the loop, and it doesn't come out when you pump it. Okay, so unless you flush it and clean it, you can't get rid of it. And this is what's happening with the very clean loop and clean gas. And basically what we did was we spent about a week to get this sort of condition on a palladium wire. So these are times, and this is the resistance ratio of a 10 centimeter palladium wire. And we put it in the loop, and right after we've run one of these cells and we flushed it, you won't have any hydriding in this wire. And as you clean the loop, you're coming up to this point where this is a 2-minute hydride for this 0.1 millimeter in diameter wire, and that is pretty much theoretical diffusion rate. So that's when we ran the last one. So is it just that we need to clean the loop? That's part of the factor here. And another part of the equation is that what we've done is we've raised the voltage up. Okay, so here we're running under the normal conditions, and I think the rate would look something like that. Over here, what we're doing is we're running it under much higher voltage conditions, like 10 kilovolts, and at lower currents, so it's not heating as much. So what has happened here, and I think there's a discontinuity, and what that's due to is a lot of ions coming out of the chamber. That's not really normal for this case. You don't see the ions being propagated to the ion counter from the plasma. So there's something unusual going on here, and this one gave us that's a very recent result, and it's a fairly large result for us. A couple of the other things that we do are after the water, after the loop's been run, we'll wash the cold trap out if we put any CO2 in. So these are CO2 runs, and we'll look at the counted sample. Okay, and this is the D2O combined from the gas. It has about 220 ppm in it. And these are the samples when they're corrected for the water dilution. This is the raw data. This is corrected for water dilution. This is sort of the enhancement over this 220. So what we expect to see is 220 ppm, and what we're getting is these sides. Now, I don't really know what the CO2, if the CO2 is so innocuous, why is all the tritium going to it? Well, this is maybe actually a fairly practical spin-off if we can concentrate the tritium in this way. So we'll have to do more work with that, but it's an interesting side effect. One of the other things that we've done is gamma count all of the samples, and typically what we've seen in the foreground versus the background is just the pair annihilation, the lead X-rays, the potassium-40, actinium, bismuth, this sort of thing, maybe some uranium from the counter, germanium, cosmic ray stimulated peaks. So we haven't seen any gamma rays yet. And I think we will see gamma rays when we go to much higher tritium generation rates, but I think at these rates we'll just have to do better. The other thing that we've looked for are other elements on the electrodes by XRF. Okay, by XRF. And that's been a little bit spotty. We've seen some aluminum, but I don't think there's any reason to believe that that's not something that's already just in the material, or could come from the system. And we've seen antimony, and that could be from solder, which was used in some of the other ones. Right now we're spot welding everything. So in conclusion, what I'd like to say is that we haven't seen any tritium at low pressure. We've seen reduced tritium at high temperature. These hydrogen additions don't enhance the effect. The surface modifiers are important, but they're not enabling. And we have to make sure that after we run one of these cells, we clean the loop up. And this is of course, a big problem, because that inhibits the number of samples we can run. We've seen a reduction in tritium output if the palladium is annealed or stress relieved, so we want a stressed sample. These alloys can produce tritium, and that's kind of counterintuitive to what we first were thinking, in that we only got tritium out of the pure materials. And is this segregated material more effective than homogenized material? Well, we have 3 batches. 2 are segregated. 1 is homogenized. The one that's homogenized that doesn't do anything, the other 2 do. Is that just because there's a lower concentration of palladium, the rhodium in the palladium, or is it because it's actually got these little islands of rhodium-rich material? Most of the tritium is found in the gas, so we're looking at surface effects here, and about 30% is found in the palladium after you dehydrate it. And we have this very large non-equilibrium between the water and the gas concentration. If the CO2 is added, and we have to look at that to see what the implications there are. When we did that high voltage, low current plasma experiment, we did wheel up a neutron counter to see if we had any neutrons, because we were a little bit concerned about that. And there were no neutrons over the background, and we haven't seen any gammas. So I think what this study is saying is that here's a robust method if you do everything right for screening materials. It's very easy to do the experiment. In fact, this experiment, which gave us a pretty good rate, was only a 20-hour experiment, so this is not a very long investment. So a lot of alloys can be screened very quickly this way, and I think we'll be running through a number of other alloys that we feel are likely candidates. If you have any that you want me to run or want me to make, let me know, and I'll certainly put them in the queue. So I want to thank you for your attention.
Questions? Yes, Dr. Martin.
I have two questions. Let's see, the first one is this geometry. If I were going to implant with a plasma or something, I think this is the last geometry I could pick. There must be some good advantages for it that I don't see. That's one question.
Okay, let me go ahead and do that one. Okay. The big advantage is that we have tried other geometries. Okay, and they're more difficult to fabricate. They use more material. This only needs 30 milligrams of this alloy, so we don't have to make a whole lot of the alloy. Also, this plasma, as indicated, only goes up halfway, so it doesn't touch any other material other than palladium or whatever this wire is. And that's a big advantage because we don't sputter all sorts of impurities.
The other question is, other than the fact that the NRL seems to be a black hole for cold fusion experiments, why didn't theirs work when they tried to do
that I think was partly due to the fact that we ran out of the good batch of palladium. We had this batch of palladium, we were getting these fantastic results. Everything was very nice. We enticed NRL to come in and try and replicate it, and then we used it all up by the time they started, and we had to send them our sort of second string batch, which gave us those very weak results. And then if you run a couple and the system isn't clean, I think you're going to get zero after that. So you have to clean and hydride. And they never do this really critical hydride experiment. And we, at that time, we knew the gas was good, but we really didn't appreciate this, whatever the hydride inhibitor is that builds up. Okay? And when we switched gas bottles, we noticed that we weren't getting anything, and so we thought our gas was impure, but it turns out it's just a loop artifact. So, how things are. Okay, it's research.
Good job.
You claim that stress relief reduces tritium production. Do you have a quantitative estimate? What kind of residual deformation you have when you see it?
That is one of these. What we've done is on the Goodfellow wire, we've stress relieved it by heating it at 600 for maybe an hour. Okay, so it goes limp. Okay, and there's maybe a 3 times 3 reduction in the tritium output, but it doesn't go to zero.
Another question, sorry,
Can you show the curve you had the most tritium produced?
One of these.
Show how high it goes.
Yeah, I don't show how high it goes because it doesn't go up too much higher than this. Okay. And I already had this other view graph, so I just chopped it off so it fit. It's too bad.
Well, I think that's enough for that one. Thank you very much, Dr. Claytor. And now we have Dr. Mori, who's going to talk to us about some transportation experiments. I start with distribution doing light water process. Dr. Mori. Very useful.
Today, in this presentation, I'd like to talk about the work entitled Isotopic Distributions of Heavy Metal Elements produced during the light water electricity on all the areas.
Dr. Mori, I think probably you should use the microphone because you're not very easy to hear.
In a previous presentation, we reported that iron was produced on and in gold electrodes during the light water electrolysis at the current density of about 200 milliampere per square centimeter. and the amount of iron was in the range of about 10 to the 16 atom per square centimeter. And the isotopic distribution of iron atoms was evidently different from its natural isotopic abundance. After that, very recently, we found that porous black or gray deposits were produced by the electrolysis at current rate is about 200 milliampere per square centimeter. And major component of the deposit was gold. Besides mercury, platinum, iron, silicon, and fluorine were contained. The isotopic distribution of mercury, iron, and silicon were significantly different from their natural isotopic abundance. And a lot of the microcraters were formed on gold surface after the electrolysis. In the present presentation, I'd like to talk about these experimental results. The experimental condition we use is as follows. Electrolytic cell is quartz glass cell. Working electrode is gold plate sprayed with the glass fragment in order to make strained surface. And its electrode surface is about 1 square centimeter apparent area. And main impurities containing in electrode is as follows. Counter electrode we use is platinum electrode. Main impurities is as follows. And solution is 0.5 molar sodium sulfate or 0.1 molar sodium carbonate solution. And main impurities is as follows. And the temperature is 21 plus minus 0.1 centigrade. Typical deposit we obtained is shown in this figure. In this figure, the black spots are the deposits. These deposits are placed on nickel plate in this case. This is the figure of the deposits enlarged at 30,000 times. These deposits are very porous and having a lot of nanometer order pores. Next, I'd like to talk about our experimental results. This figure shows relative concentration of elements with mass numbers from 180 to 204 containing in deposits and electrodes before and after electrolysis. In this figure, concentration is shown in logarithmic scale with arbitrary units. And solid line shows element concentration in deposits. And dashed line shows in element concentration in electrodes after the electrolysis. And dotted line shows that before electrolysis, that is background sample. In this figure, in this mass number range, the outstanding elements are platinum and gold and mercury. The content of gold is largest in every deposit. This is the smooth spectrum. This data is obtained from smooth measurement. Relative concentration of elements with mass number from 50 to 70 are shown in this figure. In this mass number range, the outstanding element is iron. In this figure, zinc also seems to be great. However, in this mass number range, these particles overlap in signal. So, accurate determination of zinc is difficult. Perhaps the real concentration of zinc would be smaller than this level. The relative concentration of elements from 23 to 44 is shown in this figure. In this mass number range, the outstanding element is silicon. The isotopic content of silicon present on and in the gold electrode are very close to natural isotopic abundance. However, silicon present in a deposit is different from natural isotopic abundance. So that the silicon contained in deposit is also considered to be the reaction product, perhaps nuclear reaction. This is the relative concentration of elements in mass number range from 1 to 10. In this mass number range, the outstanding element is fluorine, the amount of which is fairly large. This element would scarcely be present in natural environment if we don't add artificial. Therefore, this element is considered to be the reaction product by the electrolysis, not coming as impurity. We consider. Typical OT spectrum of the deposit is shown in this figure. As seen from this figure, mercury signals is observed together with gold and platinum signals. After sputtering about 5 minutes, mercury signal disappears. However, in some cases, mercury signal remains even after 10 minutes of sputtering. This is a typical EDX spectra of the deposit. In this figure, this is the spectrum of deposit, and this is the spectrum of pure gold. In this spectrum of deposit, we can see only a little widened signal of gold. However, by subtracting pure spectrum from this deposit spectrum, two clear pairs of platinum and hydrogen are observed. From this result, it's clear that a considerable amount of mercury is present in a deposit or in a deposit. In addition, this spectrum shows the presence of osmium, judging from the increasing of the spectrum in this energy region. The presence of these elements is confirmed by EPA measurements. This is the EPMA image. In this figure, this is the same image of the deposit. And these three figures are EPMA of gold, platinum, and mercury. As seen from this figure, the ETMA of gold is most bright. So we consider that the main component of the deposit is gold, and therefore these deposits are produced at gold electrode, we consider. And as also seen on this figure, platinum and mercury is contained in deposit by nearly same amount. This ETMA shows the ETMA of iron, silicon, hafnium, and osmium. In this figure, iron and silicon is containing in deposit. However, as seen from this figure, osmium is containing a considerably large amount of osmium is present in deposit, and small amount of hafnium is also containing in this deposit. These elements are extremely rare in natural environment. So we consider that osmium and hafnium is not impurity, but produced by electrolysis, perhaps nuclear reaction, we consider. Next, I'd like to talk about the isotopic distribution of several elements. This figure is isotopic distribution of mercury present in a deposit from 1 to 15 scan by Schmidt analysis. As can be seen from this figure, this line is the percentage of 200 mercury, and other mercury isotope percentage is in this region. As can be seen from this figure, mercury 200 increases significantly from its natural abundance level of 23% to near 50%. On the other hand, mercury 200 decreases significantly from this natural isotopic abundance down to around 10% or so. This is the isotopic distribution of iron present in the deposit. In this case, as I had presented last year's presentation, the isotopic abundance of 57 increases strongly from its natural isotopic abundance of 2% up to over 50%, especially in the surface parts of the deposit. On the other hand, iron 56 degrees strongly. This is the case of silicon present in deposit. In the case of silicon, the electrolysis was conducted in sodium sulfate solutions at a current density of 800 milliampere. And mercury and iron case, the electrolysis was conducted in sodium carbonate solutions at a current density of 500 milliampere. as seen from this figure, silicon 28 decreases, especially in surface, near the surface layer of deposit. And on the other hand, silicon 29 and silicon 30 both increases pronouncedly.
What does scan number mean? Portion of depth?
Since running time.
Time.
Time. 1 time, 3 time, 7 time.
Same as depth.
You have a guess how deep is 15?
Does it indicate depth in the electricity? And how much would that be in depth? I mean, angstrom?
I accurately calculate. I'm not accurately calculate. And
can you give us
I can't answer
a rough order of magnitude? Order of magnitude?
Order of several thousand angstrom or so.
1,000 angstrom?
Yes.
For each scan. Each scan 1,000 angstrom off.
It's one scan, it's the time that it pours in.
And question,
15 scans,
I'll answer
1.5 micron, is that what
after
I'm asking?
presentation.
Does Dr. Mizuno know anything about this?
Yeah, I can say that.
2,000 angstrom.
When again 2,000.
Yeah, okay.
Next, I'd like to talk about the electrode surface after the electrolysis. The electrode surface after the electrolysis reveals very strange characteristics. This electrode was obtained after the electrolysis in sodium carbonate solution for 30 days at a charge density of 500 milliampere per square centimeter. As seen from this figure, many microcraters like this were formed. This is called electrode surface. The diameter of this crater is about 20 micrometer, and the height of deposit crater is 30 micrometer. This is the upside view, and this is horizontal side view. This is the structure of crater, of inside walls of the crater. This is downside, and this is middle side of the crater. Inside this crater, we can see that the wall consists of many hexagonal clusters. And middle side, inside the middle part of the crater, the wall is consists of also hexagonal cluster. But in this case, the size of crater, crystallite, is much smaller. And the structure of the outermost walls of crater is very likely to that of the deposit. Likely to the structure of the deposit. The presence of the hexagonal crystals shows reconstruction of wall and suggests that some elevated heat is evolved at this crater.
3 more minutes.
So the deposit will spewed out of the crater as the ash when producing such crater. Perhaps this crater was produced by nuclear reaction, and nuclear reaction is occurred at such a site. This is the distribution of crater of gold electrode surface. As seen from this crater, the crater is developed along the scraped edge of gold electrode surface. From this experimental result, we can assume at present stage the following possible scheme. First, gold react with hydrogen to form mercury, and the mercury is very unstable and decompose platinum and osmium in one way, and in other way, platinum mercury decompose and produce iron, and iron decompose silicon and fluorine. At the present stage, we consider such a mechanism, but this is very it's not conclusive mechanism. To make reliable mechanism, much more experimental will be needed. Thank you.
Right, certainly some very interesting results. Just one question, if I may, myself, and that is, I'm not quite sure I understand about the solution. You analyze the solution for impurities, did you? And was there? Could you relate any of the impurities in the electrode to impurities in the solution which could have diffused in?
The purity of solution used is as follows. Most impurity is silicon oxide, 5 ppm. Next, iron 0.05 ppm, and mercury 0.05 ppm, and other elements not detected. So this concentration is very low. So I don't consider the result obtained is not influence such impurity.
Have you analyzed it after the run? The solution? That's before. What about after?
I not analyze after the solution.
He didn't do it. John Dash.
Does the solution dissolve the quartz cell?
Quartz cell dissolved in solution.
Yeah.
Yes.
I don't determine experiment, but in the quartz glass, the concentration of iron or above elements is very small. It's well known. So such effect is very small, I think.
Other questions?
You report approximately 10 to the 16 atoms per square centimeter. Can you relate a rough thickness so we can get atoms per cubic centimeter? How many atoms per cubic centimeter? Yes, you report 10 to the 16 atoms per square centimeter.
What was the volume concentration?
The volume concentration is 100 milliliter.
100 what?
100 milliliter. ppm.
ppm. There's some other questions on this paper.
Over what weight then? It's so many ppm. What's the total weight of the electrode? This is per. I'd just like an absolute number of how many grams of iron is produced. How many grams of iron is produced?
What's the weight of electrode?
Weight?
Yeah, weight.
the weight, I don't measure the weight of
Roughly, is it 10 grams or 100?
electrode.
Yes.
No, the electrode is about the area of electrode is about 1 square centimeter, and the thickness is
1 millimeter?
4.1 millimeter. So the weight is
Multiplied by 10.
very, very about 1 gram.
So you can get something out of that. Yes.
Could we just get the volume of the solution so we can take be able to get the total amount? What's the volume of your electrolyte?
100.
Thank you.
Now, I don't really see any other hands raised, and we're going to have a little break now, so we can talk about our
new developments reported here, exciting results. So what we want to do now is open this for questions and discussion. I have had the request for several short presentations, and I've told people they could do that, but we have to limit that to about 5 minutes. One person who wants to do it's racing over to have overheads made, and we'll be back in a minute. Is there anyone else here who would like to make a presentation? Did I get a see your hands? I thought there was somebody else. You would like to make one, and who else? Could we, I think it would be good to start with those, so if you would give yours, and perhaps the other one will be back in time. Meanwhile, in addition to listening to this, put your thinking caps on for questions, comments, and so on. I'd like to have a very interactive discussion.
Okay, this was something I was not able to present the last time, I'm sorry. It was just to make a plea for consideration in any research that you are considering for transportation, to really consider the use of Brown's gas as a new method of analysis. And the reason for, I think, it being so interesting is that the machines that produce brown gas exist. They are available from China, and they are repairable. They're known units. But what is nice about brown gas is that it is dynamic, so you have something flowing all the time, and you can regulate if you wanted to eventually for further experimental purposes, pulsating and the pressure and so on. And this might give a new dimension to any reactions that may lead to transformations. And a new dynamic. Because as I understand it, electrolytic cells are quite static. And this is my saying, why don't we try to have a new approach to experimentation? Yes, Mr. Decker?
They have a website on the internet. You can download an awful lot of details about Brown's gas. It's PrimeNet @@seung/home1.html. I'll write it down if you want it. Just do a Netscape search and type up Brown's gas, and it'll come up and give you the address.
That was mainly the thing. I don't know anything, that was what I was hoping to. Okay. Yeah, that's about it. So I don't, unless you have questions, at least to focus that topic. Okay, thank you.
Let's see, the other presentation we'll have to wait a moment on, so I would like to open this. Yes,
well, I think this might be a good way to start the discussion. I invented what I'm going to say right now in the last 3 minutes, but I thought to myself, well, if I think back and I not look at the notes and so on, what stands out to me about what I learned at the meeting? And I got the following points that may stimulate disagreement, etc. I think that as far as clear formation of elements, nuclear formation of elements in the coal, Mizuno, Omori, Dash. It seems to me those three papers all say the same thing, that under electrochemical conditions, you deposit things, and there is, by some mechanism, details of which are unknown, inside the electrode, more than 10 angstroms or 30 angstroms deep, nuclear reactions occur and produce a number of new elements. And I think the evidence of that is very clear. Then I think, secondly, evidence for nuclear activity of another kind. I think the papers of Claytor, which have now been published for the last 4 or 5 years, in ever-increasing detail, but they always say the same things, I get tritium, are very, very clear in what they say. And today we had, or yesterday we had, spark and X-rays. So I think that's very clear evidence of nuclear activity. And thirdly, but perhaps I should put it firstly, we do have what people always say we don't have. We do have a theory, and I think that Dr. Kim's theory is a sophisticated theory. Sometimes I think it's too sophisticated myself, but at any rate, it's a sophisticated and serious theory which he's been developing for some years and which has come out in various forms. But I think that and the Hagelstein theory are two very serious theories of the cold nuclear reactions. Now, perhaps another person might take another slice through the results, but those are mine, the ones that impress me.
Could I start by trying to bring some controversy? First of all, it seems to me that if you look at the new data from Mizuno, Nori, what I presented to, and so on, with the array of isotopes, neither of the theories that you mentioned address this in any way, and so I would dispute the argument we have a theory. I think we now have a database developing from which a new theory will evolve.
Well, I asked Dr. Kim that's something which is relevant to what you just said. I said to him at the end of his talk, I said, but how can you explain people who get a dozen new elements developed inside an electrode? And he replied, Dr. Kim, he's gone.
He's there.
Would you like to add something here?
Well, I'll tell you my part on it. It seems to me that Dr. Kim's theory is wonderful for penetrating the barrier, but it says virtually nothing about what's going to happen thereafter. And these processes that seem to be happening include fission and things of that sort, which
my position is that
his theory is mute on.
My position is that if you want to build the pyramid, you have to start from the bottom. And eventually, so I'm not ready to very, say to you that I have an explanation for it. But I have a theoretical framework from which I can start working on.
He hasn't gone as far as you want him, as you ask him. His theory can't yet stand your question, but it's a penetration in, and it's a framework, as he just said, which you might go further. And we haven't had that until the last year or two.
I think that's a tremendous advance.
Yes, so do I.
I'd like to suggest a consideration a bit of Paul Rowe. Did Paul Rowe ever show up?
Could you stand up and maybe asking people to say who they are? They don't know each other.
Working with explosives, and he found that every time they detonated the explosives, there was excess hydrogen that should not be accounted for by the chemical composition of the explosive. So his company is working for, dismissed him. So he set up a reactor in his own basement. He'd put in elements that had no hydrogen. He'd use a hot wire and explode them, and he would get hydrogen. Went back through the literature and found there was this anomalous production of hydrogen reported from 1905 on. And so he came up with the idea that if you have an explosion, it kicks the ether in the button. The ether responds by dumping out protons and electrons. So I had the temerity to suggest that if you've got a micro explosion in a metal lattice, then perhaps the ether, which none of us believe in, of course, the ether can dump out a proton electron near the nucleus. perhaps preferable to the nucleus, and therefore you penetrated the Coulomb barrier. Geez, what an elegant explanation of how to get around the Coulomb barrier. Of course, I haven't found any buyers for it, but if there are any,
just have a brief second. Historically, I'm reminded of this by Paul Rowe. Paul Rowe has written a paper about 1913 and cold fusion. And he quotes several papers that were written in 1913 in England around J.J. Thomson, of course, a very famous originator of the electron and so forth. And J.J. Thomson comments upon the products of the discharge tube. The products of the discharge tube have too much helium, xenon, argon, etc. Where did they come from, he says. In those days, people used to write very loquacious papers, and it goes on and on for several columns, talking about where this stuff came from. He said it must come from inside the electrodes. Perhaps there's the rare gases inside the electrodes, this gas discharge tube. And then he says, in pregnant work, he says, I am sometimes, this is a rough memory, but I am sometimes forced to consider that there might be some happening, like there is in radioactivity, whereby new elements could be produced. Now that, I think, is the first suggestion in 1913.
I have a question related to Dr. Miley and Dr. Mizuno's work that maybe someone like Professor Bockris could answer. If you electrochemically implant, elements into a metal, do you see normally any isotope segregation, or do you not tend to segregate the isotopes?
Well, there's a well-known theory in classical electrochemistry. Electrochemistry has been around for 20 years, 25 years, of isotope separation. So the simple answer to your question is yes. However, although hydrogen, deuterium, and tritium have very large separation factors of the order of 10, and so the proton deposits at 10 times the rate of the deuteron, say, other elements, higher atomic weight, where the differences of the isotopic masses are like 52 to 54, so there'll be very, very tiny preferential depositions. And indeed, as I've just been discussing with Dr. Umori, many of these things are seen deep inside the electrode, 2,000 angstroms, 10,000 angstroms deep, and solid state diffusion in a weak couldn't possibly account for it. So the answer to your question is yes, but no.
Yes, I'm sorry. Could I make just a comment on that? I think that's a very good question. And I think what we've heard just now is a type of reasoning which all of us in this room have to be very careful of. Because basically what he's saying is we know everything there is to know about isotope separation and diffusion. Therefore, all the theories about nuclear reactions are wrong. And I think one ought to consider the possibility that maybe we don't know everything we need to know about diffusion and about isotope effects, and that they might play a role in this.
I'd like to comment on your comment based on what I was doing. That is, my objective with the thin films, which I feel represents a marvelous way to do quantitative measurements in this, is to get a mass balance which would show that forget about isotope ratios and all of that, to show that you produce more of a given element than you had coming from any place else. And so that's why I'm reporting micrograms, absolute numbers. There are larger uncertainties on them than I'd like right at the moment, but I'm trying to improve that. So I'm not yet ready to feel that we have to rely completely on isotope ratio arguments. And in fact, since we don't know what the reactions are, maybe there shouldn't be large isotope ratios occurring. It could be closer to natural, depending upon which reaction is creating this.
Yeah, I think your point about a total mass balance is absolutely correct, of course.
Yeah, and also O'Malley reports on the order of 100 times more elements positive on the surface than all of the he measured previously. So.
But that's not a total mass balance.
Well, it's 100 times more mass in created what appears to be created on it.
But the assumption is that that mass came from somewhere, and you have to therefore prove that the mass is missing that it came from.
It wasn't in the cell anyway.
Those elements weren't in the cell. 100 times more of certain elements in the solution.
I think Dr. Miley would agree that that doesn't constitute a mass balance measurement.
Just a quick historic note. It was from it was Deborah Rollison, I believe, wasn't it, David, at the first cold fusion conference that suggested